So I want to use differentials to approximate the given value by hand. So we're going to approximate f of 3.1 using differentials for the function f of x equals x squared. And what do we know? We know that f of 3, if we plug in 3, we get 9. Okay? So x changes from 3 to 3.1. We're going from 3 to 3.1, right? We're using this information here to help us approximate f of 3.1. So the x value changes from 3 to 3.1. Therefore, delta x is equal to 3.1 minus 3. So the change in x is equal to 0.1. So delta x is 0.1. Now, if we know how much the y value changes from f of 3 to f of 3.1, okay, then that is the definition of delta y, okay? Now, we can approximate delta y with dy, okay? So dy is defined to be delta or f prime of x times dx. So I'm going to approximate this with delta y or dy, which is f prime of evaluated at 3, okay, times dx. Now, what is f prime of x? Well, if the function f of x is x squared, f prime is a derivative of x squared, which is 2x. Okay, so I'm literally going to take 2 multiplied by the input of 3, so 2 times 3, times delta x, which dx is my differential, which is 0.1, the change in x. When I multiply that out, I get 0.6. So dy is 0.6. So the y value changes by about 0.6. So what does this mean? F of 3.1 is approximately 9, which is the output of f of 3, plus, well, how much did dy change by? It changed by 0.6, so I'm going to add 0.6 to my output, and I get 9.6 as my answer. Okay? So why even bother with doing this? We could do this by hand, right? Like if I just took f of 3.1, I literally take 3.1 and I square it. There's nothing difficult about squaring 3.1. 3.1 is 9.61. Hey, that's really close to what we approximated, right? So 9.61 is really close to 9.6. So regardless, this was a pretty good estimate to within 100th of the true answer, right? So why do we even bother with this? Okay, in most real life situations, we don't know the function that describes some particular behavior. So we don't know why the particle moves the way that it does. However, what we can do most times is we can only take measurements of how things change, okay? So measurements of the derivative, that's what we're talking about. So it's like, okay, at time 2, the molecule of water is heating up at a temperature of 71 degrees. At time equal to 3, it's 78 degrees. At time equal to 4, it drops back down to, I don't know, 71 degrees, right? So we may not have a function that models this. However, if we take all we're given are just measurements of how it changed from one point to the next point, right? Maybe we are just told like, hey, look at this. At time 1, we had, it increased 2 degrees. At time 2, it decreased -1 degrees. At time 3, it increased 3 degrees, whatever, right? So we might just be given measurements of a derivative, right? How it changed. So this is why we bother with differentials, because in real life we don't just get handed some function that says f of x equals x squared. Okay? So this allows us to measure the change using calculus in real life situations. So Euler's method is a method that you will learn more about in differential equations, but this looks at small differentials to estimate the path traveled by some particular solution. So we have some particle, okay, and we take a little differential going in one little step there, and then we take another differential, and we take another differential, and we take another differential, okay? So maybe the original path was like this, okay? And so this black path here that we have, this is the estimate of that true path, all right? And it's a pretty good estimate. The smaller your differential steps are, the more accurate you will be, okay? The bad thing about Euler's method is if you have some curve and you've got big differentials, so you're starting here and you take a differential here, and then you take another differential, you take another differential, you take another differential. And what happens is you might slowly get off the further you go. The more differentials you take, the worse your estimate gets. So the idea is if I make my differentials really small, then I will be able to follow the path better. So the bigger your differentials are, the less likely you're going to be able to stay on that path, okay?